Hi everyone, I am Sambhu Vandai Sharma from Triveni University, Nepal, and I am very happy to present my work here in ANPA Conference 2021. And my topic is a comparative study of structural, mechanical, electronic, and optical properties of pristine and fluorinated hexagonal boron nitride monolayer. So these are the contents of my presentation. Let's begin with introduction. And at first, background of this particular material, hexagonal boron nitride (HBN). The HBN is a non-magnetic insulator. It is experimentally synthesized by several techniques. It shows excellent thermal and mechanical strength. However, the electronic bandgap of HBN is too large. In fact, it is a natural insulator and it lacks the semiconducting functionalities. So most of the boronite materials are used as insulating materials. Meanwhile, experimental and theoretical work shows that a chemical passivation is one of the best approaches to tune the structural, electronic, and optical properties and fix the large band issue of monolayer like HBN. So, keeping that in mind, we introduce the fluorine passivation or fluorination in HBN structure. It is because several literature shows that fluorination induces half metallicity in nanoribbon. It changes the electronic behavior from insulator to semiconductor, and it even induced magnetism. An interesting thing is, very recently, an experimental study shows that the fluorination in HBN structure can enhance the optical properties. Motivated by all this fact, we calculated structural, electronic, mechanical, and optical properties of this fluorinated structure as well as the pristine structure of HBN and compare. So now the theory part. For mechanical properties, we simply use the stress strain relations and use certain mathematics to fit the equations, and further we calculated the mechanical parameters like Young's modulus, bulk modulus, or layer modulus, position ratio, and so on. For optical properties, we use GDP in RP approximation in our calculations, and it is very simple. Here we calculate the epsilon or the dielectric function in terms of epsilon real and epsilon imaginary. And further, we calculate the loss function, the absorption coefficient, the refractive index, and the reflectivity, and so on. Now, here's the computational detail. We use the code CSTA and we use GJPB approximation, and we use following computational parameters. So now let's start into the result and discussion part. First, the structural property. We can see the optimized structure of both pristine and fluorinated structure on the right. The important thing to mention here is the planar structure is turned into the buckled structure after fluorination with the buckling height around 0.50 Armstrong. And we can see there the bond length is increased significantly between boron and nitrogen. And the negative cohesive and formation energy value confirm the monolayer is stable, as well as the fluorination is experimentally feasible. So now the chemical bond analysis. We perform the molecular charge density analysis and plot the valence charge density contour plot to analyze the nature of bonds in both monomer. In pristine SBN, we see boron and nitrogen is covalent, and still we see same thing in passivated structure of HBN. The boron and nitrogen is still covalent, but the fluorine nitrogen is ionic. Fluorine boron is partly ionic and covalent, as you can see clearly in figure on right. And further, we test the dynamic stability, and we found that there is no imaginary bands, phonon bands in both uh, pristine and fluorinated structure, FBNF, and we confirm that both structures are dynamically stable. And here is the mechanical stability and strength. We calculated the elastic constant using the strain and strain energy relations. We see there the strain along x-axis is epsilon x, strain along y-axis is epsilon y, and the strain energy distribution clearly in there in for HBN and FBNF clearly on the picture. And further, we found the elastic constant like C11 and C12 and C13, and we checked the bone stability criteria, and we found that both monolayer are mechanically stable. And further, we calculate Young's modulus and bulk modulus position ratio for both parameters, both monolayers, and we tabulate there in table, and we can clearly see that the mechanical parameters is reduced. especially the Young's modulus position ratio both is reduced after fluorination. And here is the orientation dependent mechanical properties. We fit the polar plot there for in-plane stiffness and position ratio, and we can see the perfect circle for both monolayers, confirming the fact that these both monolayers are mechanically isotropic. And we can see the other parameters like C1, C12, shear and layer modulus, and so on for both monolayer, and we see the mechanical parameter is slightly reduced after fluorination. And we can see that detail in the summary of the mechanical calculation there in table. And we see there the reference, which is experimental data. We are very close to the experimental data that confirms our methodology is accurate. And we see all the parameter for FBNF is reduced, especially for mechanical parameters. And here's now the electronic properties. We can see the band and PDOS side by side here for both monolayer. We can see the electronic behavior of HBN, which is insulator, is shifted into the semiconductor by reducing the band from 4.62 to 3.39, as shown by previous report. And we can see there in PDOS on the right, the 5p orbital of F element is playing main role to reduce the band gap for fluorinated structure. And now on the optical properties, we see the dielectric function at first. We can see there the epsilon real and epsilon imaginary. The value of epsilon real at zero energy gives us static dielectric constant, and we can see there is a significant increment in the static dielectric constant for the fluorinated structure, especially for different incidents. The A and B denotes the incidence of optical signal parallelly and perpendicular respectively. And we see the epsilon imaginary, the more bands, more curves are pronounced for epsilon imaginary, indicating the fact that there is more interband transition in this fluorinated structure, and more optical activity is increased. And now the energy loss and absorption part here, we can see there the energy loss function for both structure is increased significantly in both structure, I mean both incidents, and it also concludes the optical activity is increased. And this kind of materials are very useful for optical fiber and beam splitters. And now we can see the final optical parameter that are reflectivity and refractive index. We can see that the reflectivity is significantly more and pronounced, especially for fluorinated structure in both incidence of both kind of mode of incidence of light. And we can see the refractive index also increase, and this all confirms that the optical activity is significantly increased after fluorination, and all the result of this optical calculation is shown there in table. We can see there eta 0 that gives us the refractive index, static refractive index, epsilon 0 which gives us the static dielectric constant, AE which gives the absorption H, that is the value of the photon energy to create the minimum threshold value of photon energy to create the minimum optical activity. And we see the values that we calculated are very much closer to the available literatures. And we can see that for fluorinated structure, all the parameters increase, especially for perpendicular incidence, the more is the increment in optical response. And now the conclusion part, and we conclude that we can conclude that both structures are thermodynamically and dynamically stable. And after fluorination, the planar structure of the boron nitride is turned into the Buckwald structure, and the electronic behavior also changed from insulated to large band semiconductor after fluorination. And fluorination has improved the optical activity and optical behavior significantly, and this is confirmed by experimental research also. And all this finding confirms that this particular fluorinated boron nitride monolayer can be one of the best candidate for nanomechanical optoelectronic device application. For example, like high temperature processors, solid state lighting, solar cells, and power electronics. And further in future, we can calculate other chemical and thermal stability, as well as we can calculate the electronic transfer properties for this particular material. And here's the acknowledge part. We want to acknowledge the Kathmandu University for providing this high performance facility, and I want to acknowledge all the professors, my friends, and family. And here's the reference. And thank you very much. And I will be very happy to receive any questions. Thank you.